I'll blame him for a few things. I got misled by your web page of the school, and misled by no, obviously this is not what I want to do. Okay. It has two screens. Sorry. So I was going to blame Axel because of the title of that event that says school, and then the web page that says that people should have some knowledge of electromagnetism and calculus. So some of the stuff that I'll say will be fairly simple. And now that I see all the people here that probably understand MHD better than I do, I'll give you an experimental perspective of the way we think about MHD when we look at when we look at it, right? Lots of the stuff that I will be presenting can be found on the web page. Compared to what has been said this morning, starting with compressible medium and shots and all this, the experiments lie here. This is orders of magnitude away from Astro. It's getting closer to the experiments. I think I should finally move these down to here as far as experiments go. That slide is probably a little bit old, but that's what we look. And of course, the fact that the experiment looked close to the Earth is conveniently misleading, because the Earth is rotating about 10 to the 10 faster than you can rotate any experiment, right? So this is, again, not true. So Axel asked me to prepare for sorts of lectures, and I'll go in sequence through them. The first thing I'll do is talk about induction processes. It's just the way that you want to understand how MHD works in the lab. So basically, what this is all about is taking something like Keith Moffat's book or Paul Roberts' book, Chapter 1, and doing the exercise. All right. So you go in the lab, you do the exercise that what people describe in these books, and you're trying to find exactly what is being described with two things that I will discuss today. First of them is that all flows where you want to see magnetic Reynolds number effects are turbulent. So you have to deal with this. And the second is that all the flows that you want to play with in the lab are in a finite container. And the fact that it's in a finite vessel changes a whole lot of things. The second is I'll discuss small-scale issues where we try to see what turbulence does. So the first lecture will ignore turbulence, at least pretend to. And the second will discuss some of the small-scale effects that are due to turbulence in the fluids. And then I'll talk about the VKS/Cadarache dynamo findings, about what we understand about the generation of that dynamo and what we understand about the dynamics of that dynamo. And again, I apologize for those that have listened to some of these in the summer, but I haven't invented anything since then. So what I want to describe in the first series is, well, you've been through the equation now. I want to discuss a little bit boundary conditions and examples, experimental constraints, and the simple effects that how you distort magnetic field lines in an experimental. Now, there's no way to write.
Yeah, so it's crazy,
it's
right?
cool, so I was getting ready to write things on a board.
Yes, what we could do is we could move that up.
I could move that up for a little while, and fantastic. And this is convenient to avoid. So yes.
Hopefully we can get a better fit shot here.
I want to see if I write on that side. All right. The first thing that I'll write against the induction equation, right? What I'll be trying to describe today is induction processes. That is, you apply a magnetic field on a flow of a conducting liquid. In a lab, that means a metal, and we'll come back to it. And then you try to measure and understand how those magnetic field lines get distorted by the motion of the flow. All right? And what induction, potential currents, everything that comes out of the fact that when there is motion on the magnetic field, then you get induction. All right? And now, some things you can do, you can solve it analytically when in the very simple cases, and almost everything that was possible to solve simply nowadays you can find in several textbooks. Or you can try to, in more complex situations, you won't be able to solve it analytically. So you have to find ways either to simulate what's going on, or to get yourself an idea, a picture, when you look at that bunch of fluids. You know, let me say this just off the start. An experiment, and Agris has been discussing this, I know, and he's one of the fathers of doing all this, is a bunch of liquid metal. If you're in your own little lab, it can be a gallium, or a gallistan, which are good conductors and not so difficult to handle. Or people use sodium. Sodium only melts at 100 C, then it catches fire when it sees the air, or water. Water, it explodes. It's even worse. So you're on top of trying to do experiment, you're sitting on a small bomb, which you want to be careful with. And what you can measure is a very few things. How many things that hydrodynamics knows how to measure, or magnetohydrodynamics knows how to measure into a molten metal above 100 C is not that much, right? So when you want to do this, and the reason why you have to do this is that the number of degrees of freedom that you have in a flow like this will not be in any near future solved by a computer simulation. So you have to get yourself some idea what's going on. And either you can solve the analytics or you can think about what's going on, right? And so what I'll try to describe is a few ways to think about the processes that take part into the moving fluid. So, you know, of course, that these can be changed into B grad U minus U grad V. Now, beyond the math, that's trivial if the flow is incompressible. Beyond that math is the fact that these are the two induction processes that one learns about at school, and it's fairly useful to remember them that way. This B grad U is just deforming a circuit in a constant magnetic field. So you have a loop circuit, all right, and you change its shape into a magnetic field that is constant, you create an induction. And this here is that you're moving a circuit into, or you're having a stationary circuit into a magnetic field that is varying. Okay, you can take a circuit moving into a region where the magnetic field is changing, and that produces induction. And those are, I'm sorry to say this, but when you think about your experiments, you really want to go back to things like this. You really want to understand how it works, and those are two major processes. That is, again, changing the shape of loops into a constant magnetic field, or changing the field with a given loop. Another way to think about it is, in your mind, to try to draw a small circuit, okay, and look at how the motion will eventually assume that that circuit that you put into the flow is carried with the flow, and try to figure out how that circuit is deformed and what induction processes work on them by the fact that there will be an electromotive force which is equal minus d phi dt. Here is one that you can solve analytically. Here is an exercise. And that exercise is at the heart of the Lawson-Wilkinson dynamo. You are rotating the cylinder, okay, in a medium that has the same electrical conductivity sigma. All right? And you impose a magnetic field line which is along the axis like this. And you try to see how that differential rotation is going to shear the magnetic field lines. We'll come back to it, but that's fairly easy to understand. If you have differential rotation, you will do this to the magnetic field line, therefore creating, all right, that's a magnetic field line, that's a differential rotation, I'll come back to it again, and that's what he's going to do to the magnetic field line. In doing so, you started with a magnetic field line which is along the axis here, and you twist it and you create a toroidal component. Well, this is simple and fair enough, right? Now, try to solve, and these can be solved exactly. It's not a simple calculation. It's in a paper by Erzenberg. 55, Chris? 54?
57.
It's 50. So it's Erzenberg. I think it is 58. 58? All right. I'll try if Axel has a list of people here. I'll send a list of reference of the stuff that I've been using and presenting. So it's not such an easy calculation, right? Now try to change the game a little bit so that sigma is still the same all over the place, but the permittivity mu is changed. So here it's mu1 equal to mu naught, say, outside, and it's mu2 equal to something else in the cylinder. All right? And do the exercise. Now, it's a hard one. It's one which I don't know the answer analytically, but a lot can be gained if you again draw a little circuit here. Imagine that that circuit is being twisted with the motion, in which case the flux is going to be changed, and that will produce a current, right? It's always same. Now, the flux that is being changed is given by the amount of twisting, and the current is given by curl H equal J. And that's the first clue of how things are going to change. Think about it, we might discuss it again. I'm sure we will discuss it again at some point. So this was the boundary, this was the simple induction equation. And again, I apologize. The second thing that I want to say about this is when you look into these two remarks on the boundary conditions. What people usually use as boundary conditions, if you go into textbook, they all explain to you how you draw little circuits like this, and you let them go to zero, and there you find that, as I don't know, B normal is continuous, or you draw a little circuit around the discontinuity, and you find that the jump in B is linked to the surface current that it may eventually flow on over. All right. This is nice, and this certainly is analytically true, But what you want to do in a real experiment is you want to look at the currents. What is important is how the currents flow into the medium. So when you want to simulate, because you don't really have a flow and the outside boundary is insulating. You don't have that. That doesn't exist. There's no plastic that I know of that has zero electrical conductivity and that holds a sodium flow at above 100 C. Okay? So what you have is a flow, a layer of metal, most of the time it's stainless steel, all right? But stainless steel doesn't have zero conductivity. It has small conductivity with respect to the sodium. Small doesn't mean zero, and the effects you're after most of the time are small also. So neglecting this is a problem, and tracking this means you run simulations where you track the currents. So really what you want to do is you want to follow the currents, the electric potential, and so on. And this is what you want to know about your experiment. Yes?
Sorry, aren't there any ceramic containers used?
You could have a ceramic container, but it has another drawback. That's a good idea and a good question. It has a drawback. That vessel here is also the heat exchanger. Okay? Because these things are heat machines. All right? They produce more heat than anything else, right? So you start a flow. Because of viscosity, that flow produces heat, and you got to take the heat out, otherwise the temperature runs away. Okay, and it has to be a good exchanger. Actually, because of that reason, a lot of experiments run into a copper vessel, which in that case is not a small electrical conductivity with respect to the sodium. I'll come back to. Now. Because of that, of those boundary conditions and the fact that the medium is not always insulating or perfectly conducting outside, you want to care about the fact that both permittivity and conductivity may depend on position, right? Now, if you want to derive that equation again with those two functions, if I... All right. I'll write it, and I hope it's not wrong. That's what you end up with. Okay, that's the usual stuff, which normally is 0. And because of all these terms, now what you have is yet the curl of H is J, and in Ohm's law, those two things, that's all right, there's B over mu, those two things are a function of position. You end up with the number of terms that are, so it's gradient of the log of mu sigma times curl B plus the curl of the gradient of the log of mu sigma times B. This one's a funny one. It says that the log of mu is some sort of velocity minus the gradient of the log well, the first one is the gradient of I think it's only sigma. Log of mu sigma times the gradient of the log of mu cross B. Anyway, that's what I got this morning. I think it is. I think it is correct. There's one more term when the conductivity is not uniform. Mu is uniform, and there's a few more terms where the magnetic field is not uniform. Interestingly enough, in that case, with an equation like this, it's pretty hard to show that some theorem are being preserved. Like, for instance, Scaling's theorem holds, but it's not a simple matter to show that it holds with an equation like this. I want to check. I think it's only log a sigma. I'll rederive it again tomorrow.
Because the mu is inside, right? I mean, the mu is really belongs under B.
Excuse me?
B, the mu originally.
No, I think there's only a sigma here. There's an effect that you get even when mu is constant, which is the jump. They're almost, this is the other lesson when you write this, they're almost equivalent, but not exactly. And the reason why not exactly is the fact that the boundary conditions at the jump says the electric field and the magnetic field attach differently. Okay, so the effect they produce on the currents cannot be the same. All right, they're almost the same. All right, then I'm sure you've discussed. I think for a moment I can not use the board. So how long do I have?
Until 1/2
Until 1/2. All right, see where we are, and I'll pick up from that tomorrow. Liquid metals. All right, for those of you, all right, there's only 2 liquid metals that are worth playing with, and it really is a shame that Kerry Forrest is not here, because he's been advocating and considering the fact of doing MHD experiments in plasmas in the next few years, and that's a very, very interesting proposal. One of the major advantages of plasmas would be that the magnetic Prandtl number can go up to 1. Okay? Whereas in all liquid metal experiments, the magnetic Prandtl number is incredibly small. All right? So this is, I believe, to be the case of gallium, and this is sodium. The difference is an order of magnitude, I mean, a factor of 2.5 in the diffusivity. The magnetic Prandtl number is about the same, but then the density is widely different. And the reason why we care about density is the following one. What you want to do is, if you want to see any MHD effect, you need mu sigma Lu, which is the magnetic Prandtl number, to be of order 1. Okay, of order 1 if you want to see anything, of order 10 if you want to see some nonlinear effect, and of order 100, give or take, if you want to see a dynamo, that is an instability. Okay, it's true for any parameter in any unstable thing. Order 1 you'll see something, order 10 you start being nonlinear, order 100 you'll see a bunch of instabilities. So the instabilities that you want to see here is the dynamo. So, but then you got to be careful about the Reynolds number of the flow, and the Reynolds number of the flow is Lu over the viscosity. And that's the magnetic Reynolds number divided by the Prandtl number. That is, if this is anything like 1 or 10, and this is anything like 10 to the 6, 10 to the minus 5, this is like 10 to the 6, which means fully developed turbulence. Actually, the kind of flows that people play with in this line of research is as turbulent as the largest wind tunnels there is. Okay, you got the full turbulence problem, for which we don't understand so much, on top of a full nonlinear MHD program. All right, and that's what you have to play with. And there's no assumption; it's all there. It's inside the volume you're playing with. So if you do this, you could compute. Being the experimentalist, you could compute how much power, how much watts do you need to produce that flow. Okay? Because watts is amount of heat that will go in, things like using ceramic containers, they're all related to this. And you could compute, so the power in fluid mechanics, a large Reynolds number does not depend on viscosity. It's just how much you have to pay for shaking thing. All right? Shaking means mass times velocity squared divided by time. Okay? So that's how it has to scale. So it has to scale like rho L squared U cubed. All right? That's the scaling of how many watts you're going to put in thing. That immediately tells you something. If rho is 1,000, L is 1, and U is 10, okay, you're playing with a megawatt. All right? So if you manage to do it for less, it's all good. And more is going to be complex. A megawatt is like a TGV head train, right? It's pretty good to play with. All right. Now, you choose, most of experimentally starts by choosing L. L is a very good measurement of your engineering gut. Okay? You want to make things bigger, it's going to be more demanding engineering. You make it small, well, when it's too small, it's very demanding engineering, right? So there's the range where you know you can do the engineering, right? You usually end up with L equal of the order 1. Because an experiment that will be 10 meters across is too big, and one that would be 10 centimeters across is too small. So you end up, basically, that's what you can do. Once you've done that, you got U. The U you can achieve, given the number of watts, is rho L squared to the 1/3. Okay? This is the velocity. You've choose that. Okay? You choose that. That's the velocity that the watts are buying you. So the magnetic Reynolds number that you just purchased is mu sigma P L over rho to the 1/3. Okay? Oh, and as I've said many times, that's when depression hits the experimentalist. Because mu sigma, all right, mu, short of finding ferrofluids that are conducting, we don't have that many, is a given value of, say, mu naught. Sigma, you can make it the best conducting fluid you can think of. And it's worth working on it because now it's linear. Now, all the other, it's useful to reduce the density, but all the others enter to the 1/3. That is, multiply the power by 10, okay, is only going to buy you twice the magnetic Reynolds number. Okay? It's worth spending a minute thinking about it in terms of experiments. When you, in most instability processes that people have worked on in hydrodynamics, you find yourself a control parameter like Faraday instability, Telequette instability, Van Karman Street, whatever. You find yourself a control parameter, usually the Reynolds number. You increase the control parameter until you hit the instability. Okay? Now, in that particular case, you don't increase the control parameter to arbitrary value. You hit a wall which is given by the amount of power you put in a thing. And the amount of power is just not only the size of the grains. The amount of power is all the engineering and everything that goes with it. I don't know of any experiments now that has run more than 3. What is Karlsruhe? The pumps in Karlsruhe altogether at 300 kilowatts?
Yeah.
And that's about the same thing you have in Riga, right?
200.
200. Yeah, and the experiment we have in Cadarache operates with 300 kilowatts. And all this is not because we guys copy one another. It's just because that going tens times that is not feasible. So you know what is your maximum control parameter. So what you do is you try to fit what you want to see below that. Okay? You have an axis with control parameter, right? Here's the wall. You want to see an instability, you got to bring it in there. You do not crank the control parameter until you hit it. All right? It's a completely different philosophy. You have to design and operate the whole thing so that it will go into what you can see. Of course, in doing so, there's no free lunch. You'll have to do compromise on things, right? Okay, that's what I wanted to see about the experiments. Now, a few words. So on everything I'll describe, I'll be using the Von Karman washing machine. It's I don't know why the people came up with the washing machine name, because it's as bad as you could ever be for washing. It's a tearing machine, a shredding. You should call it the Von Karman shredder. It's probably for a good shredding machine. So it's a cylinder, okay. In a gallium flow in the lab, it's typically this size. In a sodium flow in a bigger experiment, it's typically that size. It has two propellers, discs, that rotate at the top and the bottom of the fluid. And basically, when you only rotate one disc, what you have is the disc which is rotating is acting as a centrifugal pump, so it's ejecting fluid on the side. Since it does that, it has to pump fluid in the center, and the whole thing rotates. Okay, so that's the maximum helicity type of flow in the center. Of course, the fluid goes back with the opposite motion on the other side, so it has the opposite helicity near the walls. All right. Now, you could counter-rotate the two propellers. In each case, in the vicinity of each of one, you would have that nice helical motion, and in the zone in between, you have differential rotation. Okay, and there isn't any more idea into doing all this that when you read any conventional textbook in MHD. People seem to agree that shearing and helicity are two major players in the dynamics of magnetic field. And when you read much of the talks that you've seen and listened to, people still wonder about helicity and what it does and differential rotation, which happens in stars. So you try to put a flow where you have those basic ingredients, and the first task, I guess I'll describe in the next few minutes, is do these simple processes, do they exist? How do we see it? Now, for the rest of this, I will ignore the turbulence. I will assume that the flow that you have in the washing machine, the Reynolds number 10 to the 6, is this one, with the nice swirling motion and the nice tearing motion. You can laugh if you want. This is not true, all right? This is approximation. But the reason why it may work is that in a liquid metal, where the Prandtl number is so small, the cutoff length at which the currents get dissipated is much smaller than the length at which viscous dissipation changes the fluid motions, right? So that, in a sense, in a liquid metal, the magnetic field is a slow beast, all right, which is being acted upon by a fast flow, all right? So you have a slow field with a fast forcing, all right? And at order 1, what we'll do now here is restrict ourselves to the slow behavior. So anything we will measure, we will take the average value in time, and we'll only discuss that. I will not discuss fluctuations in the first part of the lecture. Let me come to the last thing. The last thing is, what do we measure? That's deceptively limited, right? And that's the whole reason for this field is going to advance only if the numerics and the experimental people work together. There is so little we get from the experiments that we need the feedback of numerical experiments and the other way around on things that could be measured. So what do we do in a liquid which is melting at above 100 C? Well, we put little plungers like this inside, and with those little plungers we measure the magnetic field at a few locations. Alright? Maybe you can put 2. Alright? Okay, you can 3. But I'm not going to go up to 100, right? So I have no mapping of the entire velocity field. Okay? Or no mapping of the magnetic field. On the other hand, the diffusion length is like 1 over mu sigma f, f being the rotation at which I rotate the disk of the order square of the order of, okay? And this is either the size of the box in a Gaussian flow or a fraction of the size of the box in a sodium flow, right? So I don't need that big a resolution, okay? The result being that the magnetic field is slow, all right? And if I move it and I measure it here, I have a good indication on what's happening in the neighborhood of the order of that size, okay? But not a complete mapping of the geometry.
So what limits the number of probes that you put in? Because these probes, I mean, the flow is a mess anyway, so it's not, the fact that it's going to alter the flow is not exactly a problem, is it?
Well, first, you have to put it in, okay? Because some components of B don't go out, right? The toroidal, this, right? So you got to put it in, and so every time you have to open, I mean, you have to a leak-proof way to get into the flow, right? So any leak-proof phenomena is not so easy. And the number you can put is over, I don't know, we have 6 at the moment. But so there are 6 positions from which you can put probes. And one of the things that other people have done, like Carey Forrest, because he's using a sphere, or the people around Philippe Cardin and Claude Nataf in Grenoble, is put an array of magnetic probes outside and try to reconstruct the pattern of the magnetic field from outside, and then compute the Gauss coefficients and go back to what's inside. All right, but in any case, it can. The limitation is engineering, I guess, to this, and the reconstruction is the inverse problem limitation to it, and that's for the magnetic field. Now, for the velocity field, it's complicated because there's very few velocity measurements. There's basically let me finish with the magnetic field. With the magnetic field, there's basically 3 to 4 kind of technologies you can use. You can have Hall probes. You can put coils to measure the change in the flux around coils, but then that will only give you the fluctuating quantities. You can have Hall probes, you can have giant magnetoresistance probes, and you can do flux gates, which is differential flux between 2 little coils. And that's it. Most of them, except from some Hall probes, you need to cool them. That is, every time you go into the flow, you need to bring the cooling with in order for the electronics to operate at the temperature that the electronics like. When you don't, we've done that a few times. When you don't, when you get the probes out, you could get a little bit of dirt down the fingers you put in, and it's everything that has melted and burned, which is sitting down there inside of your probe. You really have to cool. And not only do you have to cool, you have to regulate the cooling, because in electronics it's very sensitive to temperature variations. Now, for the velocity, there's inductive measurements. So the principle is you put little electrodes, and you measure the potential difference between electrodes, and you try to relate that potential difference to the velocity. Basically, what you want to use is, what you try to use is that grad phi is u cross b, all right? or some variations of that, which of course is not true because it is J, which is minus grad phi plus U cross B. So if you have current flowing in the system, for instance, when you have a dynamo, this is not true at all. This is more complicated than this. Okay? You can use distortion of magnetic field lines like people do in geophysics, that is trying to see how the field lines get carried by the motion. If it is the fast motion, you assume that it is the magnetic field not changing very much, but it is just affected by the motion. You get back to the velocity this way, not with has limitations again. And the last thing is use acoustic Doppler measurements. You seed the flow with small particles, in general dioxides that form into the metal are enough. You don't need to add anything. And you blast a sound wave to the flow, and what is reflected is Doppler shifted by the velocity of the little tracers. And the time of travel is a measurement of depth. All right, so you blast a small acoustic wave. Now, the time for it to come back is the depth at which it was scattered, and the Doppler shift of the echo is the velocity of the scatterer, right? So you have the inline velocity along the line with all the problems of putting sound waves into this medium, but that's the only thing I know. So it's a very limited amount of measurements. So the problem is, how do we get back from a limited amount of measurements to what's really happening? You need a bit of theory, you need a lot of numerics, and you need to get yourself a picture of what's going on. And that's what I'll try to describe on the most simple examples. So, in order to do this, back some 10 years ago with a PhD student of mine, we've developed a very stupid method of doing so. So I'm doing the exercise of increasing the magnetic Reynolds number and trying to see, so from 0 to 1 to a little above that, see what are the induction processes that happen. So in all the cases I consider, I put a magnetic field line into a flow. I have a flow with a certain motion. I try to see what is the distortion of the magnetic field line, that is, what is the induction that I produce in doing so, all right? At low magnetic Reynolds number, remember, because of those constraints, is making it high, which is hard, not low. At low magnetic Reynolds number, you can sort of assume that it's quasi-static. You sort of assume that you're going to have the induced field as a sequence of as a series like this, for which at any step you can compute what is the induction that comes from the applied field. Now the field is B0 plus B1 you've just computed, and you can compute what is the induction due to that field and so on. You're assuming that the velocity field is not changing. This is low impact parameter, and you can solve that recursively, these equations, to get an idea. The important thing here is, in doing so, you access the quantities that really tell you the path of the currents and the potentials. Those are essentials. Things like in an experiment which is in a gallium flow in the lab, we know, but if you ask me what is the potential conditions you apply in Cadarache, I wouldn't tell you. Agris, do you know what is the potential condition you apply in Riga? Is the vessel fixed to a given potential? Well, we have electric.
Our effect is AC effect. So we can, of course, measure the potentials there, but the main problem is to cut out the induction in wires, which we are wires from where the signal is going to electronics, and these both parts are not easy to separate. So, but as our thing is AC experiment, not DC experiment, then problem about potentials is not
This is correct.
real.
This is correct. It's one advantage of the Riga is what you pick up is a DC, is an AC effect, so that you can always do a locking to the frequency you want. In our case, we picked all. I'll now describe. We'll pick a bunch of DC effects. In that case, you need to worry about potential. So in doing so, what you do is you say apply field B naught. First, I compute what is the electric field, quasi-static electric field, which is produced by that. Then I solve for the potential with the proper boundary condition. Then I compute the current. Then I compute the magnetic field, which is generated by the currents by the Biot and Savart law, and I repeat this. Okay. The reason in doing so, I have the order one effect. Okay, where it's induction again. So the induced field is proportional to the applied field because the induction equation times a function of the magnetic Reynolds number. So you could always do a series expansion of that function. At first order, when Rm is small, it is going to be linear in Rm, then it's going to be quadratic in Rm, cubic, and so on. And those are the effects that the building blocks of induction that people play with. And the interesting thing with this method is you can draw maps of what is the potential field, what are the currents, and if you want to change things. Remember, all of this is trying to learn how it happens so you can make it stronger. All right? The whole idea in the end is if you want to see a dynamo, if you want to see interesting effects, you have to make them happen. You cannot be satisfied with being what they are, increasing your control parameter, and wait for it to happen. You have to understand exactly how it happens in order to give it its maximum intensity and bring it to the regime where you want. And I think I should stop.
Mm-hmm. Yeah, thank you.
Question, please. It's an interesting idea. You can measure how close you are to possibly getting a dynamo and wonder maybe if you did it a little bit more you would get the dynamo. What's your experience so far? Is that actually a valid guideline? Or, I mean, if you're just subcritical, would you think you are indeed close to critical, or could there be some bad surprises? What's your experience?
No, there's...
Then it goes back down again.
Yeah, so all the experimental evidence or studies that we have is that we have no answer to that, up to what I know. Numerically, I mean, you will answer numerically, but numerically, in the numerical experiments that I've been doing with Minini, Ponti, and others, you very often see things like this. Okay, so that's your control parameter. If Rm is your control parameter, this is the growth rate. You're increasing, and boy, you wish you were doing this, but you don't. Okay. The other thing is that physicists strongly believed in, and the people here that are old enough have heard me giving talks about how we can solve all this by looking at the susceptibility. The susceptibility in general is, in linear theory, is the response to an applied field. So you apply a magnetic field, applied, you measure the induced field, which is the response of your system, and you divide the applied by the induced field. Now, at some point, the induced field is going to increase, so that goes down, linearly or not, you don't. So that's a susceptibility as a function of the same control parameter, and when this becomes infinite, because you hit in any phase transition, that's what you do for a susceptibility, bam, this is your threshold. All right? It doesn't work that way. You can see it, we've seen it doing, and you can, and again, increasing this is very, so you define the local slope and blah, 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 that I haven't seen it working. The other thing that you can do when you apply a magnetic field like this is look at something that people know of very easily in phase transition. It's called critical slowing down. Okay, you apply a pulse to bring your you try to excite the critical mode, and the closer you are for transition, the longer it will take to decay. All right. So if you suppose you have a field with a given geometry, all right. You apply a pulse of magnetic field with coils, all right? in the proper direction with a non-zero projection onto the critical node, and then you cut it, and you expect that the time it will take to decay will slowly increase when you get near criticality, right? Hopefully like 1 over the square root of Rm minus Rmc, blah, 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 right? We've never seen any of this. So here is decay rate as a function of magnetic Reynolds number. There's a few experiments by Dan Lathrop back 10 years ago when he was showing this. All right, the ones that we've done so far with the gallium and previous Cadarache experiments were doing this. Okay, and now we've successfully generated the dynamo, so we can go through the threshold, right? And when you go through the threshold, it does that.
I see.
All right. So I have no way, and that's a very interesting challenge. Is how do we know how close we are from a dynamo? I have no answer for this. I have only one signal which did not, and no explanation for it, which did not show no behavior. Is like the fluctuation over the mean seemed to increase near the threshold. That is, as we were nearing the dynamo and you measure the fluctuations of magnetic field, they seem to increase dramatically before settling to a dynamo state. And that's the curve we got into the experiment. But I have no explanation.
Any other questions?
Do people that work in tokamaks see any of interesting effects? Do you have any thoughts about this?
There's a very interesting way to see the reverse field pinch as a dynamo, and you can conceive what it does as some sort of a dynamo effect. But on the other hand, there's so much magnetic field applied
to contain
around you to contain the whole thing that it will be an open question, and I'll discuss briefly that. It will be an open question for people that want to do a dynamo in a plasma. The only way to contain the plasma, as far as we know, is magnetically, which means that you will have magnetic fields around. They may not penetrate far into the plasma, but you will be entangling the effect of what you apply. But when you look at the equation, only the equation of the kink instability of the RFP, it looks like the dynamo thing. Yes, please.
What's the temperature the maximum temperature in your experience that you
There's three kind of maximum temperature. This one that is engineeringly dangerous, and that's about 200 C. Okay. This one that fries the electronics, and that's about 140. Okay. And there is one where the physics starts being less interesting, and that's about 110. It's because when you're next to melting point, and you plot the conductivity as a function of temperature, and this is 100 C, okay, it drops rapidly near the melting temperature, and rapidly is not very much, right? But let me come back to this. It's your only linear parameter. Okay, so any change of this is linear. Yeah. All right, it's like you're using 20% power.
So you have good cooling of Cadarache?
Yeah, we have good enough cooling.
Yeah, and heating, of course. All right, any other questions? If that's not the case, then let's think from we reconvene at 11 o'clock for Unbus.